In this video, we're going to talk about the second fundamental theorem of calculus. So remember how the first one defined what a definite integral was? Well, this one just defines that differentiation and integration are reverse processes. This says that if you take the derivative with respect to x of the integral from a constant to x of f of t dt, where t is just a dummy variable, then this should equal f of x, right? Because again, derivatives and integrals are reverses, so in theory, they should cancel out. And if we work out this left side, we can see that this is true. So we're going to evaluate the integral first. So we have the derivative of, so now when I take this integral, I'm going to call this big F of t. And we have to evaluate this from a to x, right? And this is, remember how we said with the first fundamental theorem of calculus that the definite integral from a to b is the same as big F of b minus big F of a. That's exactly what we're going to do. So we have big F of, here the top is x, minus big F of a. And now we have to take these derivatives, like so. So obviously, if you take the derivative of big F of x, which we got from an integral, this will be the normal f of x. But this, notice how we're plugging a constant into the function we got from integration. And so if you remember from the video on definite integrals, this gives us a number or a constant. And the derivative of a constant is 0, so this goes away. And now we see we're left with f of x. This works for anything you put. It doesn't just have to be x, it can be x squared, x cubed, but then we have to expand the theorem a little bit. So this is specifically when we have x. Now, if we go down, we say derivative with respect to x of the integral of a to, now we're going to call it a function, g of x of f of t dt, then this is equal to f of g of x times g prime of x. And again, I'm going to work this out to show you why it's true. We're going to take the same process as we did with the last proof. We're going to evaluate the integral. So I have big F of t evaluated from a to g of x. And when we do this, we have to take the derivative of f of g of x minus derivative of f of a. And so you'll remember this is a constant, so the derivative of a constant is 0. But now we get to this. What is this? It's a composite function. And how do we differentiate composite functions? We use the chain rule. So the way we differentiate this is we have little f, and we keep the inside the same, and then we have to multiply by du, or in this case dg, or g prime. I'm going to write it as f of g dg. This looks a little nicer. If you have a function, then you have to apply the chain rule when using this theorem. So the derivative of the integral from a to g of x of f of t dt is f of g dg. That's the second fundamental theorem of calculus. All right, to close the video, I have 3 examples for you. So let's begin. The first example, we're asked to find the derivative of the integral from 0 to x of t cubed plus 5 dt. So we're going to begin, or first of all, before we do the work, we can use the shortcut and say this is x cubed plus 5, according to the theorem, but let's do the work for it. So we have d dx, integral from 0 to x of t cubed plus 5 dt. And as always, we're going to evaluate the integral first. So we have 1/4 t to the 4th plus 5t evaluated from 0 to x. What we get when we plug this in is we have derivative of here 1/4 x to the 4th plus 5x. And then notice that if we plug in 0, this is 0 and this is 0. The derivative of 0 is 0. So this is all that remains. And now we can go ahead and distribute the derivative here like this. And then this is equal to x cubed plus 5, which matches our answer here. Second problem. Now we have a function as the upper bound. Using the theorem shortcut, we can say this is sine of 3x squared times 6x. But as always, we're going to make sure. So we have derivative of the integral from 0 to 3x squared of sine t dt. This is the derivative of, so now the integral of sine is negative cosine. So we have negative cosine of t evaluated from 0 to 3x squared. And when we do this, we get derivative of, here I'm going to split the one term at a time. So if we plug in 3x squared, we get negative cosine of 3x squared. And then minus the derivative of, so if we plug in cosine of 0, we know cosine of 0 is 1. So and this becomes negative 1. We have minus derivative of negative 1. But as we know, the derivative of constant is 0, so this really doesn't matter anyway. Now we have to take the derivative of this. This is where we use the chain rule again. dy du is sine of u times du dx is 6x. And when we substitute for u, we get sine of 3x squared times 6x, which is what we predicted with the shortcut. So for this, notice we have functions on both endpoints. So what do? Well, we just do exactly what we've been doing. Just now we're actually differentiating both the top and the bottom term now. So this is the derivative with respect to x of, so the integral of e to the t is just e to the t. So in e to the t evaluated from 2x to x cubed, like so. And when we do this, we get, so if you plug in x cubed, we get derivative of e to the x cubed minus derivative of e to the, plug in 2x, that's e to the 2x. And then notice we use the chain rule on both of these now, since neither of them is a constant, so they don't go away. So derivative of this is e to the x cubed times derivative of x cubed minus e to the 2x times the derivative of 2x. So altogether this is 3x squared e to the x cubed minus 2e to the 2x. And notice this is f of x cubed times derivative of x cubed minus f of 2x times derivative of 2x. So now we've seen that in the case where we have both ends are functions, we can simply just do something similar to here, except now we do it for the upper bound and the lower bound, and we subtract because of the definite integration rule.